Leaving groups. In substitution and elimination reaction, the substrate is normally alkyl halides, where halogen is the leaving group. How good the halogen is as a leaving group depend on number one, carbon-halogen bond strength. The greater the size of the halogen, the lesser the overlap, the weaker the bond strength, and stronger is the leaving group. Number two, the basicity of the leaving group. If the leaving group is a strong Lewis base, then it is a bad leaving group because in the case of strong Lewis base, the donating electron pair is more interested in bonding rather than leaving. If the leaving group is a weak Lewis base, then it is a good leaving group because the donating electrons in this case is least interested in bonding and happy remaining isolated. Iodine with lowest electronegativity seems to be a better Lewis base, which is not the case because the donating electron of iodide is in a larger orbital, which has lesser capacity to overlap, or in other words, to form a covalent bond. So iodide is the weakest Lewis base. The pKa values of conjugate acids of the leaving groups are given here. Negative pKa value means strong conjugate acid, which in turn means that the leaving group is a weak base and an excellent leaving group. Positive pKa values mean weak conjugate acid, which indicates that these groups can hardly act as leaving groups and are bad leaving groups. For example, the hydroxide ion is a very bad leaving group. However, under acidic condition, a proton is attacked by electron pair of the partially negative oxygen atom of the OH group, resulting in a formal positive charge on the oxygen atom, making it a good leaving group. Another method of making OH group a good leaving group is to react the alcoholic substrate with paratoluene sulfonyl chloride, commonly called tosyl chloride, or methane sulfonyl chloride, commonly called mesyl chloride, in presence of pyridine. Now the tosylate group or the mesylate group which is formed is a very good leaving group because tosylate and mesylate ion is resonance stabilized. Stability of carbocations. Stability of carbocations is an important factor to guide us how substitution and elimination reaction proceed and what will be the product of the reaction. To understand this, we should have conception of hyperconjugation. A carbocation is sp2 hybridized. That means the carbon atom has an empty p orbital perpendicular to the plane of the carbocation, which is ready to accept electrons from the vicinity. While judging which electron is more close to the empty p orbital, the distance is not a factor. Rather, the angular separation of the orbital having donating electrons with the empty p orbital is a vital factor. This is understandable because distance doesn't matter if the total space is very small. The interacting orbitals should be properly oriented. That is, their angular separation should be minimal. In primary carbocation, these sp2 hybrid orbitals are bonded with s orbitals of hydrogen atom. Now the angular separation of these orbitals with the empty p orbital is 90 degrees. So there is very less chance of these electrons interacting with the empty p orbital. The carbon atom attached to the positively charged carbon is sp3 hybridized, and so this carbon is free to rotate about this bond. At a particular conformation, the sp3 hybrid orbital comes in line with empty p orbital, where the angular separation between the two become minimum. Now, these electrons can interact with the empty p orbital. By this way, the positive charge gets delocalized and the carbocation becomes stable. The positive charge is more delocalized in secondary carbocation, making it more stable than primary carbocation. This is called hyperconjugation. By the same reasoning, tertiary carbocations are even more stable. Stability of alkenes. In alkenes, hyperconjugation is possible if one or more of the double bonded sp2 hybridized carbon atoms are substituted with alkyl groups. Consider this monosubstituted alkene. This carbon is sp3 hybridized and this carbon is free to rotate. At a suitable conformation, these bonded electrons can interact with this sp2 hybridized carbon, because sp2 hybridized carbon is more electronegative than this carbon, which is sp3 hybridized. Thus, the pi electrons get more delocalized than non-substituted alkenes. This is called no-bond resonance. The possible no-bond resonance structures of propene is shown. By the same reasoning, we may conclude that a tetrasubstituted alkene is more stable than trisubstituted alkene. A trisubstituted alkene is more stable than a disubstituted alkene. A disubstituted alkene is more stable than monosubstituted alkene. And a monosubstituted alkene is more stable than ethene, where there is no substitution.